Hello there and welcome back to this video series on control systems. We started considering second order systems and we derived the response of second order underdamped system subjected to step input. We have seen that an underdamped system exhibits oscillatory behavior and exhibits overshoot when it is subjected to a step input. In this video, we will consider the step response of a critically damped second order system as it is subjected to a unit step input. Once again, I would encourage you to watch these videos which give a background on Laplace transforms. It wouldn't hurt to watch them 3 or 4 times. Each one is max 10 minutes. So spend about 30-40 minutes reviewing Laplace transforms. That would greatly help you because it will give you ease in going through the equations. Carefully take notes and solve all the problems mentioned in these videos to get the most out of each of those subsequent videos. We'll try to repeat some of the slides that we have seen earlier with a view to give you more ease rather than disturbing you. We have seen this is the transfer function for an example that we considered, and we said that these poles give us something about the transient response and stability. We have seen that these poles are obtained from the equation denominator equated to 0, and these are two roots, with one with plus sign and one with minus sign, and depending on the discriminant we call it underdamped system. When discriminant is negative, when it is equal to 0, it is critically damped system. Greater than 0, overdamped system. And we said we can generalize it by defining a natural frequency and damping ratio. Damping ratio is the ratio of actual damping present to the critical damping. This 2 root jk is critical damping. We saw this epsilon and omega n describe the system completely. We say that when epsilon is less than 1, system is underdamped. This is what is the system we considered in the previous video. And when it is equal to 1, it is critically damped. That is what we will show in this video. When epsilon is greater than 1, you say it's overdamped system, and we'll consider in a subsequent video. So we'll start with considering epsilon is equal to 1. When epsilon is equal to 1, we can very easily see that the denominator here, s square plus 2 epsilon omega n s plus omega n square, this turns out to be s plus omega n whole square. We will put that here. Okay, this 1 over s comes from the step input. We split again using partial fractions as given over here, and we get the value of a is equal to 1, c is equal to minus 1, and b is minus 1, because if you equate coefficients of s square, you have a square here, you have b square here. So a plus b, there is no s square term. A plus b is equal to 0, so b is minus a, which is minus 1. So you have Laplace transform of the output is given by these 3 terms, 1 minus something minus something, and taking inverse transform, we get 1 minus e power minus omega n t and all the subsequent terms, which we can simplify like something given here. This, if we plot, appears to be something like shown here. You can see it quickly raises and reaches the step input. This one is the step input. Okay. Thus we can say that a second order critically damped system does not exhibit overshoot when it is subjected to step input, and it doesn't exhibit any oscillations. And we can also see that when time t tends to 0 in this equation, when time t tends to 0, though there is a term t here, this exponential e power minus omega n t decays much faster than t, and in any case, because it's a negative exponential, when time t tends to 0, ct tends to 1. Okay. Thus, we can say that a critically damped system also tracks step input. So, in summary, we say that a second order critically damped system neither exhibits oscillatory behavior nor exhibits overshoot, and perhaps it is the fastest non-oscillatory response, and it tracks step input. I think that's all we have for now. Have a great day.